So you guys, um, we just did comparing to proportions, right? And so when you're doing proportions, you have to remember to use z-tests, right? You have to remember to check greater than or equal to 10 is the magic number when you're doing proportions, right? So now we're back to means, and it's what you've already learned, except we have 2, and we're finding the difference in those means. So remember these x bars. What do the x bars stand for? Yeah, this is what you got in the sample. So not the true mean, that's what you got in the sample. So we have to check some stuff between the difference. So first of all, the shape. If they tell you that both populations are normal, then you can just say it's normal without checking anything else, right? If they say that both populations are normal, you're good to go. You don't have to do anything else. Okay, next thing you can do, though, is you can actually just check if they're above 30. What if they tell you there's a skewed population, but you still have above 30? Are you good to go? Yes. Do you guys remember why? No? The central limit theorem? Do you guys remember that? So even if your population's skewed, as long as you have large counts, all right, you're good to go. And then, of course, we still have that you can check both graphs. And remember when you check both graphs, yeah, you can still have slight skewness, right? You just can't have strong skewness.
Yes, you can.
Yeah, you can't have strong skewness, and you can't have outliers, or I guess you proceed with caution, all right? Proceed with caution. All right, so the center, you guys. For the center of, so this is the mean of x bar minus the other x bar. If you know the true means, then you can just subtract the true means. And of course, if you don't, we subtract the x bars, right? So if we don't know those, we would do this to find our center. And typically our null hypothesis is 0, just like we did before when we get to that part. Alternate is if one is greater or less than or different. All right, and then we've got the spread. So our standard deviation, and these should have little bars over them. Okay. So this is a new formula that you're going to want to memorize. It is on the sheet, but I think they give it to you like this, and you have to be able to switch these out if you don't know these, all right? So first of all, when you've got sigma, that stands for the population standard deviation. Do we typically know the population standard deviation? No. All right. Okay. So anyways, we're going to take our standard deviation and square it and divide by n1, which is the number of our sample. And our other population standard deviation and square it, and this just stands for the second one. And then divide by the number in the sample, and it's the square root of adding those. This comes from the fact that you always add variances and square root even when you're subtracting, which we learned back in like chapter 3. And don't forget, of course, to check the 10% rule, which we've been doing a lot of. So, wait, I wanted to, oh well, we'll do this one first. All right, describe the sampling distribution of x bar minus x bar. So, a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with mean of 27 ounces and standard deviation of 0.8. When the medium setting is chosen, the amount of liquid M dispensed follows a normal distribution with a mean of 17 ounces and a standard deviation of 0.5. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each 20 cups filled with the large setting, and then 25 cups filled with the medium setting, and we're going to find the difference of our sample, large, sample, mean, medium, and then we're going to find the difference in the mean amount of liquid. So what is the shape of the sampling distribution? This one's pretty easy. What's the shape, you guys? It is normal. Okay, why? Because both the populations are normal. So we don't have to check anything else. We can say normal because populations are normal. Okay. All right, find the mean of the sampling distribution. So the mean means the mu of x bar 1 minus x bar 2. So it's the mean difference between the two. We actually know the true mean, right? So we're going to use that in this problem. So we want large minus small. So the true mean for a large is 27, and the true mean ounces for the medium is 17. So we've got 27 ounces minus 17 ounces gives me 10, and this one we can put our units on here, ounces. All right, and our standard deviation formula. So this is one of the odd cases where we do know the population standard deviation, so we can use the previous formula. Okay. So on the top is the standard deviation squared. So we'll start with the first one. The standard deviation was 0.8. And we're going to square it. And then we divide by the number in our sample. So 0.8 was our large, right? So how many large cups did we do? 20. Okay. So our sample, first sample size was 20. All right, and then the medium cups standard deviation is 0.5. So that goes in the numerator. We square it, and we did a sample of 25 medium cups. And this gives us a standard deviation of 0.205 ounces. Okay. So we could use a z-statistic only when we know the population standard deviation, which we don't normally know, and that's why we typically do what instead of z? T. Okay, good. So if the normal large sample condition is met, we can standardize the observed difference and obtain a z-statistic, right? Only when the population standard deviation is known. So you guys, normal, remember our old formula was like x bar minus the mean divided by the standard deviation. Similar formula, except now we're doing the difference in our x bars. Sorry, those should have bars on them right there. Okay, minus what we assume the difference is according to the true mean, divided by the formula we just learned for standard deviation, which uses, again, population standard deviation. That gives us a z-score. Okay. So just like we did last time, we talked about standard error for proportions. That's when we replaced our p's with our p hats, right? What are we changing this time? Yeah, our standard deviation. So SE stands for standard error. That's just what it's called when we don't know the population standard deviation. And we just substitute it out for S, which is typically what's going to happen. So S is the standard deviation of what? The sample. So it's the standard deviation from the sample, which is typically how this is going to work. And so if we do not know the population standard deviation and we're using S instead of the last formula we just did for Z, we're going to use the formula for T, which is really, really similar, right? And so we're finding the difference in our sample means, and we're subtracting the difference in our true means, or what we assume our true means to be, and we divide by the standard deviation or the standard error, where we use S, sample standard deviation. And again, this is called a t-statistic. When you're doing t-statistics, you have to remember to always state degrees of freedom. That's kind of the difference with the Z. You don't have to do that with Z, but with T you do. Do you guys remember how to find degrees of freedom from before? What? Yes, it was n minus 1. Now we have two sample sizes though, right? All right. Same conditions for inference. Some of you are forgetting, you guys, when you're doing two, whether it's proportions or means, to also say independent random samples. And some of you are just saying independent. You still have to say random, okay? So same thing we just talked about. Probably don't need to write all those down. So degrees of freedom. Yeah, you can thank some awesome mathematician for that formula. We're actually not going to use it. So I just wanted you to see, like, that's the legit formula right there. So there is one, and yay, you don't have to do it. Oh, great. So you'll most likely get a decimal from it. Now, our calculator actually finds this for us. Of course it does. So the most accurate is that our calculator will use this formula, right? The only way to do the technology part is to actually use the test or when you're doing confidence interval, just like we were doing before, right? So you'd have to do the whole thing, and then it will tell you the degrees of freedom. So you can't, like, get there first. So you'd have to go do the test and then go back and do the degrees of freedom. So either way, you have to state it. There is another way to do it, okay, which is to use the smaller sample size, and this gives you a more conservative, so in a confidence interval, you'd get a bigger confidence interval, so it's a little less accurate, all right? So the smaller of the two. So in the last problem, we had n equals 20. We sampled 20 of them, and we sampled 25 of them. So what would our degrees of freedom be? Yeah, we would take the smaller one and subtract 1, and our degrees of freedom would be 19. So the safest bet is the smallest one, subtract 1. All right, but most likely you'll use your calculator and you can state the exact degrees of freedom, but don't be surprised if it's a decimal answer, because it comes from that really super fun formula. Yeah. Mm-hmm. Yep.